Good morning, this is Dr. Kumar Arya, Associate Professor in Department of Chemical Engineering at IIT Jalandhar. Today I am going to explain the derivation of momentum balance equations in rectilinear coordinate. So if we see the momentum, the equations, so rate of change of linear momentum is given to force. So the momentum of the system, it can be given into velocity into the mass. So if you have the differential volume of differential mass, so you can put here dm. So differential force would be equal to the mass into acceleration part. So mass into acceleration, so this df equal to dm db upon dt. So this is differential acceleration part. So we can write dm here. So this acceleration will become the total derivative of the velocity, or the material derivative, or the substantial derivative. So this is given by u del v upon del x plus b del v upon del y plus w del v upon del z plus del v upon del t. So these first three terms is being known as convective accelerations, and last term is known as a local acceleration, and total of all these four terms is called total acceleration of the particles. Now considering this is a differential volume of dimension dx, dz and dy, and for this we want to derive our momentum equation for this case. So we are considering in that case, let the stresses at the center of the element are sigma xx, sigma yx and sigma zx. These are the stresses, all three stresses in x directions. So this is direction x, this is direction x, this is direction x, and this is the plane. The first coordinate is always plane, this x plane, this y plane, this is the z plane. So we can rest of the faces here, we know here this one. So this side and this side, top and bottom, this front and back can be calculated from Taylor's expansion of these one. Differential volume of this is dx dy into dz. So if we calculate the normal stress on left side would be sigma xx, this was the center. We did Taylor's expansion into minus dx by 2 is this, the outside. Then the right side is this, again sigma xx plus del tau xx upon del x dx by 2. This is the property derivative multiplied by distance traversed. So this is Taylor's expansion first term only. Then on top plane is tau by x plus sigma plus del tau by x upon del y dy by 2 in x directions. Same thing on bottom plane is minus, this is again in x direction minus. Then on front tau zx plus d tau zx upon dz by 2 in z directions. Then back direction tau zx minus del tau zx upon del z dz by 2 is minus z directions. So the directions can be finalized depending on means on magnitude and the direction of the planes. The combinations of the two can give you the directions. Means if this magnitude and plane both are of same sign, then direction would be plus. If they differ, then direction would be in the negative side only. So the total force in x directions would be dfx would be, this is the total plane, this is x direction, positive x, this was force in the negative x direction. So the difference of two would be next force in direction x. Same way for y, this is x component in y plane, this is minus x component in bottom plane. So difference of two would be next force in x direction again. Now this is again that front and back. So this is in plus x side, this is minus x side. Difference of two would be net force in x direction here. So if we simplify this, we will get dfx equal to del tau sigma xx upon del x plus del tau yx upon del y plus del tau zx upon del z equal to dx dy dz. So dx dy dz is the differential volume. So net force in direction x is the surface force dfx, which we have already calculated, plus the body force, the force of its own. So body force would be calculated rho gx into volume, differential volume. Surface force we already have. From there we have taken dx dy dz as a common here. So similarly we can write y momentum balance. This is for y direction components, all 9 this is for y. So net force in y direction would be del tau xy upon del x, del tau yy upon del y, del tau zy upon del z, dx dy dz. Similarly we can write for z direction component sorry. So z directions, direction is z, this is z, here z, and this is the plane x only. So this is x plane component in z directions, this is y plane in z direction, this is z plane in z directions. So all three. So this would be here finally del tau xz upon del x plus del tau yz upon del y plus del sigma zz upon del z into dx dy dz. Now this figure may clarify all the actually stresses. So this, if you say this one, so this is here plus the x plane, because here perpendicular drawn will go to this side, plus side. So plane is x. Now if you want to calculate its component in direction x would be sigma xx, its component in direction y is tau yx, its component in direction z is tau zx, tau xz. Now go to this side. Again the plane is x, because here the direction will go to perpendicular of this will go to minus x side. So all direction would be the reverse actually. So this is minus x side, this is minus y side, this is minus z side. Now similarly for this front part, this plane is z plane. So this is z, and the direction we are putting here calculating in x direction only. This is x, this is y direction, this is for z directions. Similarly for back side, here perpendicular to go to the minus z side here. So all direction would be the reverse here. So sigma zz, sigma zx, sigma z, tau zy, tau zx actually. Now the top one, plane is plus y, because perpendicular will go to upside. All component we are calculating x side. So this is tau yx, this is tau yy, this is tau yz. So these are all component of the stresses in different directions. Now let's see the bottom one. So in bottom one, plane is minus y, so all direction would be the reverse here. So sigma yy, this is tau yz, this is tau yx. So if we are calculating only x direction, so we should consider the component in direction x. So this is the x direction component sigma xx, this is sigma xx, this is tau zx, this is tau yx, this one here is tau zx, this one here is tau yx, and add them up so we can calculate the force. So this is the differential force in x direction is given by this equation. Differential force in y direction will be given by this surface force plus body force. Z direction would given by again surface force, body force in Z direction. This y is Z actually. So this is given by this one. Now the force is mass into acceleration, and total acceleration of particle is given by this. So this way, under steady state operations, now we can find this is total is convective acceleration. So taking the force component x by z, so you can write here this is mass actually. So the volume into density. So this is x component, y component, then z component. Now this is actually equation 1 here, and this is set of equation 2. We can equate the 2 here now. So if we equate the 2, we will get the term here rho u del u upon del x plus b del u upon del y plus w del u upon del z plus del u upon del t is equal to rho gx plus del sigma xx upon del x plus del tau yx upon del y plus del tau zx upon del z. Similarly for y direction component, similarly for z direction component. For y directions, your x is getting changed by y. So only thing here, this was here the direction here, so second coordinate the direction, so which is getting changed by y only. In case of z, second coordinate is getting changed by z only. So you will get x component, y component, and z component. Now for the Newtonian fluid, the shear stresses are given by this. Tau yx or tau xx is given by mu del v upon del x plus del u upon del y. Tau by z equal to del tau z equal to mu del w upon del y plus del v upon del z. Tau zx equal to tau xz equal to mu del u upon del z plus del w upon del y. Normal stresses are given by this. Sigma xx equal to minus p 2 by 3 mu del dot v plus 2 mu del u upon del x. Sigma yy is minus p 2 by 3 mu del dot b plus mu 2 mu del b upon del y. Sigma zz equal to minus p 2 by 3 mu del dot b plus 2 mu del w upon del z. So we have now all expressions. So here p is local thermodynamic pressures. So if we substitute that there, so our momentum equation would become like this. So we have substituted expression of normal stress and all shear stresses here, and then we are getting these equations. So again the next equation is from here, then another equation from here. So these three equations are known as Navier-Stokes equations. Now these can be simplified further. For incompressible flow with constant viscosity, in that particular term this del dot v term would be equal to 0. This will come from continuity, and therefore this equation can be simplified to this particular format. So here will become rho u del u upon del x plus v del u upon del y plus w del u upon del z plus del u upon del t equal to rho gx minus del p upon del x plus mu del square u upon del x square del square u upon del y square plus del square u upon del z square. Similarly for y component, similarly for z component. So this is the continuity equation in rectilinear coordinates. So del rho upon del t plus del rho u upon del x plus del rho v upon del y plus del rho w upon del z equal to 0. For steady state or incompressible fluid case, this term is 0. Density will come out from here So this term will become del u upon del x plus del v upon del y plus del w upon del z, which can be written as del dot v. So we can substitute here del dot v here in this one, and this one equal to 0, and we can simplify it and we'll get these equations. Similarly, Navier-Stokes equations in cylindrical coordinates. So this is continuity in the cylindrical coordinate. These are the normal stresses in the cylindrical coordinate: sigma r, sigma theta theta, sigma z z. And after that we can get the Navier-Stokes equations in cylindrical coordinate in this particular format. So you can take the cylindrical one. Then we have z component here. Now this is how we can say that del dot v equal to 0 for incompressible fluid. So you have incompressible fluid, this term is 0, take the density common here, you will get del dot v. So we can calculate how to get the sigma value here. So this is very well explained in this book, Analysis of Transport Phenomena by William M. Dean. So there they say that sigma is given by thermodynamic pressure plus a viscous stresses actually. So both of them can be added, will give you the total stress actually. So total stress would be the pressure stress plus viscous stresses here. So here for under the static conditions, viscous stresses are not there, so sigma is given by minus pi. Then here we can find the here del dot the sigma. So del dot sigma in case of net sigma is this, so is del here, so we'll say here del p for this one, then del dot tau. Then moment equation can be mentioned here that rho del b upon del t, rho g minus del sigma here, so del sigma is del p plus del dot tau. So we can write here rho, this is rho g plus del dot sigma here. So now we have the sigma is all these here 3, del upon del x sigma xx, del upon del y tau yx, del upon del z tau z. So this is the total is called the sigma actually. Similarly for y component, similarly for z component. Now for incompressible fluid we have del dot v equal to 0 from continuity. Viscous stresses for Newtonian fluids are given that tau equal to 2 mu into gamma. So gamma is given by mu del v vector plus del v vector transpose. So if you add them up you will get total stress here. So sigma is normal stress plus viscous is minus pi plus tau. So this is equal to given to by this one 2 mu gamma minus 1 by 3 del dot v vector into I. So the P is given by average of all three actually. So 1 by 3 del sigma xx plus sigma yy plus sigma zz. So normal stress is given by this. Sigma xx would be minus P plus 2 mu del u upon del x plus k minus 2 by 3 mu bracket del dot b. Now tau is given by this for the Newtonian fluids at 2 mu tau plus 2 mu gamma plus k minus 2 by 3 mu multiplied by del dot b into I, where gamma is local rate of deformation, k is dilation viscosity or bulk viscosity, I identity tensors, del dot b sum of diagonal element of gamma only. So if you find del dot b, so we can find from here EI del upon del xi Vj Ej. So dot product with delta Ij. So delta Ij would be 1 if I equal to j, else it would be 0. So we can write here del dot b equal to del u upon del x, del b upon del y, del w upon del z. Actually, so so the effect of K on fluid dynamics are difficult to detect and therefore usually ignored. So it has been shown K equal to 0 for ideal monoatomic gases, and it's generally believed that for other fluids K is always less than mu actually. So in that case we can write tau equal to 2 mu gamma minus 2 by 3 mu del dot B into I for Newtonian fluids. So we can find for incompressible fluid, this is the continuity. So we got sigma expressions minus p 2 mu upon del u upon del x minus 2 by 3 mu del dot b. So we have from here we can calculate derivative of this. So if we calculate derivative, this term is 0 from continuity. So we got del p upon del x equal to minus del p upon del x, no sorry, del sigma upon del x equal to minus del p upon del x plus 2 mu del square u upon del x square. So del dot b equal to 0 from continuity. So therefore this term is getting cancelled. Now we have tau yx, we can calculate del tau yx upon del y term from here. Del tau zx is given by this equations. So we can differentiate this with respect to z is given by this. Therefore we can get the x momentum balance here now. So this is minus rho gx minus del p upon del x plus 2 mu del square u upon del x square plus mu del square u upon del y square plus mu del upon del x del b upon del y plus mu del square u upon del z square plus mu del upon del x del w upon del z. So we can arrange the term into these formats: minus del p upon del x plus rho gx plus mu. So the second order term del square u upon del x square plus del square u upon del y square plus del square u upon del z square. Another term we have mu. This we can write del upon del x bracket u upon del x, means del u upon del x plus here you have mu del upon del x del b upon del y, here you have mu del upon del x del w upon del z. So we can rewrite this into this format. This we already have. Here we have taken the common mu del upon del x. Inside bracket we have del u upon del x plus del b upon del y plus del w upon del z. And this term is already you have from continuity. This is equal to 0. So your equations x momentum balance is rho del u upon del t du upon dt equal to rho gx minus del p upon del x plus mu del square u only. So these are the resultant equations for x direction, this is for y direction, this is for z direction. In general you can write rho dv upon dt equal to rho g minus del p plus mu del square v. X is governing resultant equations for incompressible fluid actually. So this is all about the derivation of momentum equations in rectilinear coordinate with the explanations of normal stresses. Thank you.